Hey, what's up guys, my name is Cherno. Welcome back to my ray tracing series. Lighting and shading. Everyone's always talking about lighting and shading. I mean, when I think of good graphics or photorealistic graphics and rendering, the first thing I think of is lighting. Lighting, shading, shadows, ambient occlusion, global illumination. Like sure, the quality of the actual geometry and the textures, they matter a lot as well. But lighting, that's really what it's all about, isn't it? Why is that? The reason why lighting is so important is because it's literally how vision works. If there was no light anywhere, we wouldn't actually see anything, because what we perceive with our eyes is a result of light rays actually hitting us. I mean, you don't even necessarily need to think about the human eye. Let's take a camera, for example. When we point and shoot a camera at something, the sensor inside this camera, the actual sensor, that is the thing that is soaking in all of the light that's hitting it. If there's no light hitting the sensor, we don't see anything, there is no image. And the way that the camera works is actually surprisingly similar to how we're going to make our ray tracing code work. So more on this later in the series. Because lighting is such an important topic, we will be spending a lot of this series talking about different lighting algorithms and different kind of ways for us to simulate, but also somewhat approximate and manage this kind of concept of simulating light rays hitting our actual viewport. And I am completely serious when I say that's a complicated topic. I mentioned this book in the very first episode of this series, Physically Based Rendering from Theory to Implementation. This book is filled with this kind of stuff because it's extremely complicated. There's a lot to it. Today, we're going to start our lighting journey. But don't worry, it's going to be extremely simple in the beginning. And eventually, it's going to lead us into actual photorealistic rendering, which is very, very exciting. So, without further ado, let's begin. Now, in the last episode of this series, in the visualization episode, we actually went a little bit further than we'd already gone in episode 3 with our current code base. We took a look at how to actually solve these kinds of ray sphere intersections to actually fully see where in 3D space our hit point was, and we even applied a little bit of lighting to it. I highly recommend that everyone watches that video because I think that kind of visualization really helps to provide you with a deeper understanding of how ray tracing actually works. And understanding is very, very important for this kind of stuff. So there is going to be a little bit of overlap from the kind of code that we typed out last episode in C# using Hazel and also here inside our C++ project. Now, the current stage that we are at is this pink sphere. We haven't really adjusted it for aspect ratio, as you can see, but that's okay. Next episode, we're going to talk a lot more deeply about the camera. But for today, the best thing I can recommend is kind of trying to make this viewport square. We could, of course, do this programmatically, but we're not going to bother since that's not going to really apply for future episodes. That way you'll kind of see what's going on here. Now, you may have noticed that my render time has increased slightly from the last episode or from episode 3. The reason being is I'm on this laptop, which is not as powerful as the computer that I use. So no code has actually changed. We haven't made anything slower. We're just simply running this in release mode. But this kind of rendering time indicator is just a good kind of measure of what is actually going on and if we're doing stuff that significantly slows down our code. So if we hop on over into our per pixel function that contains the actual math that's being executed over here, we've solved this quadratic formula discriminant that we learned about in the second episode. And we'll be referring to more of this episode 2 math here in this video as well. And because we know over here that if our discriminant results in a value greater than 0, we have 2 solutions. If it's 0, then we have 1 solution. If it's less than 0, so if it's negative, we have 0 solutions. Using that, we're able to conditionally return a different color. So we return pink if it's greater than or equal to 0, and of course just black if it's not. Now, if these quadratic equations aren't really quite making sense to you and you would like to revise your math a little bit more, then I highly recommend you take a look at Brilliant, the sponsor of this video. Simply put, Brilliant is my favorite place to learn math on the entire internet. They are an absolutely fantastic resource. They're a website filled with courses on various STEM topics. And unlike other course websites, Brilliant's strong points are the fact that they are extremely engaging and interactive classes. They don't just sit you down and throw content at you hoping that you'll absorb it. They actually get you to engage and interact with the content, as well as quiz you on what you've learned to make sure that you're actually retaining that information and learning. We're learning all about ray tracing here. We're learning how to render photorealistic graphics. That involves a lot of math, and it's also extremely visual. Lots of math, extremely visual. That's what Brilliant is all about. Their math courses do a fantastic job of covering literally everything we'll be using inside this series. And they've also got various other STEM topics such as computer science and data structures. The best thing about Brilliant is that you can get started for free. Just click my link in the description below. But also Brilliant have been nice enough to offer the first 200 of my subscribers who click that link in the description below 20% off an annual membership. As I mentioned, the key to this series is understanding, making sure that you understand everything. And so if you're struggling with the math at all, or you would just like to understand it more comprehensively, then Brilliant is your friend. Huge thank you to Brilliant, as always, for sponsoring this video. So ultimately the plan for today is to continue solving the quadratic formula. We've worked out the discriminant, which is this part over here that's listed as 32 here. We just need to then square root it and then work out the two solutions by adding or subtracting negative b from it, dividing by 2a, and then we'll get, hopefully, our two intersection points. Now, of course, if the discriminant is 0, then we'll get the square root of 0, which is just 0. So we'll get plus minus 0, which is the same as just not having that at all. Obviously, it doesn't matter if we subtract 0 or add 0, we'll still only have one solution. Therefore, we have that kind of, if it's 0, we have one solution section. In which case, t will technically be the same. If our code will compute two values, as we'll get it to, the two values will just be the same. Now, we are still outputting our color as just kind of an RGBA 1 byte per channel format. That's going to be fine for now. We'll have to write a little conversion function because ultimately I want to move into dealing with floats for our color values, just like we would be doing if we were using GPU shaders. Now, just because we're going to be using floats for colors doesn't mean that we can't use this kind of 8-bit per channel approach. We can. It's just that our float value will ultimately just result in a number, in an integer between 0 and 255, which is obviously the maximum kind of range we can display with just 1 byte of data. So the first thing I want to do is kind of rephrase this or replace this to actually return a GLM vec4. So if we go back to our header file, I'm going to do the same thing. This per pixel function now is going to return a GLM vec4, which is going to be 4 floats. So if we want pink, we'll return 1011, so RGBA. Just the green channel here is going to be 0, and if we want black, we're going to return 0001. Now you may have noticed here that the previous value of black was actually this, right? So we had kind of the alpha first. That's because the alpha channel occupied like the most significant bits of this actual integer. We have to remember that because it means that when we do this conversion, we'll have to shift it up to the most significant bits, which means we'll have to shift it left by 24 places to get that bit or those bits into the right place inside this memory. But it makes more sense to us if we just define the alpha channel being here so that it reads RGBA. Now, if we come back over here into our render function, now this per pixel function obviously isn't working because this buffer is still a uint32t. So this is exactly where we have to do our kind of conversion. So what I'll do is separate this a little bit. I'll have our GLM vec4 color over here. That's going to be our per pixel. And then I'm going to write some kind of like convert to RGBA function that will take in our color and output just a uint32t. Let's go ahead and scroll up a little bit. I'm just gonna make a little namespace called utils for all of these various utilities we might have, and that's where I'm going to implement this convert to RGBA function. Now, I don't really need to copy all of those floats, so I'll pass them in as a const reference here, and now we can get started. So first of all, let's just convert a single channel. So for example, the red channel, to convert that, we just need to multiply it by 255. Because what that's going to do is when color is 1, which is seemingly the maximum here, it's going to make this exactly 255, which is our maximum. And when it's 0, it's going to make it 0. Now, what if it's above that? Well, yes, technically we will get a value above that, which will probably spill out into other channels, depending on how we actually write this code. What we technically should do is make sure that that value is clamped between 0 and 1, meaning it's no less than 0, and it's no greater than 1. If we were running this code on the GPU using an API such as Vulkan or DirectX or OpenGL, it would actually be doing that clamping for us depending on what image format we're using. Here, of course, we're doing everything ourselves. There is no like graphics pipeline, there are no GPU drivers doing all this extra stuff for us. It's just C++ code, so we have to handle that ourselves. What I'll actually do is I'll scroll down over here, and before I actually provide this convert to RGBA function with the color, I'm just going to set the color to be glm clamp color, and then I want to provide it with the minimum, which will just be glm vec4 0, and the maximum, which is going to be glm vec4 1. This will clamp every single component of that vec4 to be between 0 and 1. So now we can be sure here that it is in fact never going to be 1.5 or negative 0.5 or anything like that. So once we're multiplying it by 255, we now need to convert it into some kind of integer because, well, that's not going to be useful to us at all. So what we can do is just convert it into a uint8t. That will be our red channel. And there we have it. We have a 1 byte unsigned integer type here that is now going to contain a value between 0 and 255. Let's go ahead and do this for all of the other channels. Now, I didn't really mention this about GLM, but one of the nice things about their API is that you don't have to write like X, Y, Z. You can just write RGB. It's referencing the exact same memory. It's just a different name. It's like an alias that you can use, just like in the shading languages. So now that we have all of these, let's combine them into a uint32t, which is what I'm going to return over here. So we'll type in uint32t result, and that is going to be the A channel. Remember, that's the first one that we needed to shift up 24 places. So we'll say A shift left 24. That's going to put it into that most significant byte of that uint32t. Then we're going to combine it, so we'll use a bitwise OR to grab the blue channel and shift it up 16 places. Then we'll do the same with the green channel, but 8 places. And finally, we'll have the red channel at the end, occupying the least significant bits. And finally, we can return our result. So there you go. You could do all of this on one line, of course. I've just written it out so that it's hopefully more readable. Now let's go back over here and add that utils namespace. And there we go. That hopefully should work. So let's run this code just to make sure that it's working. Remember, the big change that we've made here is that we've switched up our code in the per-pixel function to actually use vec4s instead of uint32ts. And there we go. We still see a pink sphere. Now, it's important to test and make sure that our color channels are in the right order. So I'm going to make it a red sphere, hopefully. So if this is blue, we know that we've flipped our red and blue channels. But there you go, it's red. So that is in fact correct. Okay, awesome. So now we can use floats to express colors just like we would be doing if we were programming on the GPU in shaders, which is exactly what I want. The main reason why I wanted to do this so early on as well is just because dealing with colors in floats is something that I want you to get used to, first of all, if you're not already, but also because dealing with colors as floats is just much more comfortable. It's a lot easier to do common things. For example, if you want to do like some gamma correction, that's all going to work as you would probably expect because it's in a 0 to 1 range. If you square a value that's like 10, you're going to get 100. It's not exactly what we're looking for. So my point is just that if the colors are between 0 and 1, a lot of the math that we actually want to do to calculate those colors, they actually work really well with a number between 0 and 1. So it's really useful to get into that habit as soon as possible, really. Okay, so let's talk about how we can actually solve the rest of the quadratic formula. Well, we know it's going to be minus b, negative b, plus minus the square root of the discriminant, which we already have. So let's write that part down. So the rest of this is going to be minus b plus minus the square root of that discriminant. And all of that is going to be divided by 2a. So divided by 2a, and we need to make sure that we're obviously dividing all of this. So that is the rest of the code that we effectively need to type out here. Now, this part is not useless though, because this lets us effectively early out from all of this. We don't need to continue solving the rest of this and actually running this code, evaluating this mathematical expression if there are no solutions, because our array just completely missed our sphere. So we can just return, well, you know, like the clear color in this case, but it could be just an indication that like, hey, keep going, Ray, like you haven't hit anything. So what we'll actually do is flip this around so that if the discriminant is less than 0, then let's return black, which is going to be like our clear color. Otherwise, we're going to keep going and actually calculate a color. So for now, let's define some kind of sphere color. I'm just going to make it a vec3. We don't really care about the alpha at this point in time. I'll still keep it as pink for now, just to make sure everything's still working like it was. And obviously, if I just return this now as is, I'll have to make sure that I'm adding in that alpha value as well. But at the moment, the kind of non-modified sphere color, if I run this code, I should get exactly the same result as before. I've just kind of flipped the way that we deal with this if statement here. So we've got our terms, A, B, C. We literally just need to plug them into this equation, and that's it. Now, because we have a plus minus though, we know there's going to be effectively 2 outcomes to this, and either one of them are solutions. We can find out which one is the closest hit if we want to, but ultimately they're both going to give us solutions. So let's go ahead and type in T0. That's going to be our kind of plus variant. So minus b plus GLM square root of the discriminant divided by 2 times A. Let's go ahead and surround this with parentheses so that it's clear what our division is doing, and that is in fact T0. Now T1, the other solution, is going to be minus B minus square root of the discriminant divided by 2A. That's kind of it. Let's go ahead and drop this comment down here, and we've got our two T values. Now, going back to the math episode, we know that these T values are not some kind of coordinate in 2D or 3D space. No, instead what it is basically a hit distance that we can then plug into our original ray equation, which was A plus BT. So A and B, A is the ray origin, B is the ray direction, and T is what we've just solved for. And as you can see over here, we can do this if we want per component. So we only had X and Y, we did this in 2D space on paper, but we now have a Z component. We can just calculate it for a Z component as well, because our ray origin and ray direction will also have a Z component, so this will all work. And once we have that, it will provide us with an actual 3D coordinate for each component that we have. So since we will have an x, y, z, we effectively have 3 of these equations that involve t. So we plug t into all 3 and we get an x, y, z hit position. That's our coordinate in 3D space, which defines where our sphere was actually hit. So back in our code, we have ray origin, we have ray direction, and we have t. Now there's no reason for us to actually do this per component. We don't have to do float x and type in like ray origin dot x plus ray direction dot x times t0 or t1. We could do this, that would work. However, because of the way the GLM's API works, and in general the way that these math libraries work, this isn't unique to GLM, is we can just do this same operation to all 3 components at once by just writing ray origin plus ray direction times t0, which of course is very useful. So we have our first hit position, I'll say h0, and then we have our other hit position, which is going to be this t1 here. So this is our sphere potentially getting hit twice, once on the entry and once on the exit with this ray. So if we actually wanted to visualize this in some way, which hit point would we use? Well, if we take a look at this, we know that ultimately we're calculating 2 t values, and t is like the distance from the origin along the ray direction to our actual hit point. So clearly the smallest t value, the smallest solution, should be the closest hit. So just by looking at this math, I mean, assuming that A is not negative, we would always assume that this is the smallest solution because we're subtracting a value from here and then dividing it by 2 times A. Now, if we take a look at what A is and how we calculate it, we actually use the dot product here of ray direction with itself to get A. So effectively what we're doing here is squaring ray direction and then adding them all together. So there's no way that can be negative. So A is definitely positive, and then we're doing minus B minus the square root. So T1 is going to be the smaller value no matter what. It might be negative possibly, but it will be the smallest value, especially because we obviously know that the discriminant is going to be positive. I mean, it's going to a square root and we're not dealing with imaginary numbers, so of course it's going to be positive. So T1 will be our closest hit point. I might rename it to just read closest T. So because of that, let's get rid of this other one. We're not going to use it at the moment, and this is actually going to be our hit point. Now what I could do at the moment is just output the hit point as a color. So this is what I mean. It's so easy to do. It's a vec3. It's going to be roughly in that 0 to 1 range. Most of it will be because we're dealing with a sphere that has a diameter of 1 or a radius of 0.5. And since our colors are also kind of in that 0 to 1 range, we can just set our sphere color here to be the hit point. And if we run this code, we'll get something very interesting. So we actually get some coloring here that appears to show that our sphere actually does have some depth to it. And then we have a very large blue section here because this part of the sphere is actually going to have negative hit point values because the origin 0 is here. So therefore everything left of that, everything below that is going to go into that negative space from 0. And we are clamping negative values to just be 0. So we're seeing this blue here because X and Y, so up and down is our Y axis, left and right is our X axis. Those are both 0, but Z is going to be positive, and Z is the blue color that we're visualizing here. So what's actually going on here, if you've never seen this kind of thing before, is we obviously have an X, Y, and Z coordinate for every pixel. That's the hit point. What we're doing is taking those values and outputting them as the color. So the X coordinate becomes the red channel. The Y coordinate becomes the green channel, and the Z coordinate becomes the blue channel. And so we're able to kind of visualize these numbers as colors and see, for example, that the top of the sphere here is green because the Y component of our hit coordinate is larger. And over here towards the right, our X is larger because it's more towards the right, which contributes more red to that final pixel. This kind of practice of outputting our data, our mathematical numbers as colors is very, very common in graphics programming. So that's all good. We can see that our hit points are working because we visualized them. Hopefully you can see why it's so helpful to do this in graphics programming, because the alternative would be what? Like placing breakpoints and kind of trying to look at this per pixel, or logging every color, but we have like, I don't know, 1 million pixels on our screen. It's so difficult for us to kind of look at that information presented to us in a per pixel basis and make sure it's working across our image. There's just too much data to deal with. But if we can visualize it in some way in the form of colors, we can look at the entire picture at once and see if it's working correctly. Let's take a look at this piece of paper that I have here. If it's facing the light, it's very bright. If it's not facing the light, I mean, we can still see it a little bit, but it's significantly darker. As I rotate it to face the light, we see a much brighter color. And this, of course, works in 3 dimensions. Doesn't matter if I orient it so that it faces down, it's still going to get a lot darker. And it obviously works not just for flat surfaces, but if we have something like this, my light source is over here. Hopefully you can see that the areas that are facing the light are obviously a lot brighter than, say, this area over here, which is facing away from the light. How can we take this and recreate it with our sphere? Well, let's think about the different pieces of our puzzle here. What are our different variables? We have the light. I mean, sure, there are things like the brightness of the light, how big it is, all of those other details, but fundamentally it's just the location or the direction of the light, and then also the location of our model, and possibly more critically, the direction that each part of this model faces. Now we're rendering things in terms of pixels, so we can translate this to say the direction that each pixel faces. So we need the direction of the light coming in on us, and we would like to know the direction that each pixel of this model is facing. Because if we look at this area over here, we know that because it's facing away from the light, it's facing that way, the light is facing that way, it's not really facing the light, it is in fact darker. So we have this kind of observation here that the more we face the light, the more this kind of area faces the light, the brighter it becomes. So how do we apply that to our sphere? How can we determine per pixel which way, which direction it is facing? That is called a normal. Why is it called a normal? I mean, a normal sounds like a bit of a weird name for it, because a normal is a vector that is perpendicular to a particular surface. So I have this pen here, I have this flat surface, the normal would be a vector facing up, facing that way. If I had this kind of flat surface, it was facing this way, the normal would be this vector over here. So in other words, a normal is exactly what we're looking for, because it's a vector that is facing the direction that the face faces. Lots of facing going on here. So how can we work out this normal vector for our sphere? Well, it's actually really, really easy. Since we know where our sphere's origin is, and we also know the position that we hit the sphere at, we can simply subtract those two vectors. We can take the hit position and subtract it from that center point, from that origin, and it will give us our normal. Now, we don't exactly have a sphere origin at the moment because it's just 0. So that's even easier. It means that literally our normal is our hit point, with the only exception being that we need to normalize this normal if we want to be correct. The reason being that obviously based on the origin of that sphere itself, those vectors are going to get translated, well, anywhere in 3D space, as well as the radius of the sphere. If the radius is bigger, we're obviously going to get a larger kind of vector, and that's not really a directional vector anymore. The length is going to be equal to our radius. So in this case, it's going to be 0.5, whereas we want to have a unit vector. That's actually why this image that we looked at here was so dark, because we're not looking at these colors between like 0 and 1, they're actually going from 0 to 0.5, and hence we're never exceeding that kind of 50% level of light. So going back to our code, I'm going to type in glm vec3 normal, and it's going to be our hit point normalized. Again, usually we would subtract our sphere origin from hit point, so we'd write hit point minus sphere origin, but we'll introduce that later when we actually have the ability to move our sphere around and probably render more than one sphere as well. That would be nice. So now that we have this normal, let's look at that instead. Let's visualize our normals instead of visualizing that hit position. So there we go, much brighter effect. So this is something that you should get used to. If you don't quite understand why this image looks like it does, just take a moment, play around with it, play around with some other values potentially, and just make sure that you understand it. Now, the sphere is a little small, so what I'm actually gonna do is move the camera forward a little bit. We've got this ray origin at 2, which is the location of our camera. I'm just gonna push it 1 unit forward so that we get a much larger image, as you can see here. Now, because we're actually sending those rays in the negative Z direction, the normal that we're getting is positive Z, which is why we're seeing so much blue in this image. That's a little bit annoying though, because clearly we're losing a lot of that capacity to visualize this normal here. Why? Because the normal vector is a unit vector that can be between -1 and 1 for each component. So because it goes down all the way to -1, we can't see anything past 0. Anything that's below 0 just becomes 0. So we're seeing no red at all and no green at all for like this entire region here. What I would much prefer is having like the colors be in a range that we can all visibly see. So in other words, I'd like it to be between 0 and 1 instead of -1 and 1, because that way we can at least see everything. So how do we convert this from being between -1 and 1 to being between 0 and 1? Well, we can just multiply it by 0.5 and add 0.5. That will obviously take that -1, make it -0.5, and then add 0.5 to push it to 0. And meanwhile, our positive one, which is the other end of the extreme, that will be halved to 0.5, and then we'll add back the 0.5 to bring it back up to 1, so no change there. So if we run this code, there we go. This looks a lot better to me, because we can actually see the kind of full spectrum of colors here. We can see that it gets more red as we look to the right and more green as we look up. The blue mostly stays the same. Okay, so now that we've done this, let's define some sort of light direction, and then we can use some math to compare the two and see the angle between them. So what should our light direction be? Well, looking at this image, we know that we're facing the negative Z direction. So I think our light source should kind of be also facing the negative Z direction so that we can actually kind of see it. And then maybe I want it to come from like above over here. So we want it to be going in kind of the negative Y direction as well, so that it's going down from above. And since my mouse pointer is around here, I want it to come from this side. That's also basically negative X, because it's coming in from positive X into kind of this negative X space. It's going left. So what I could do is simply just define like a directional vector that's -1, -1, -1, because that's what I'm looking for, and then just normalize it. And that'll take it to be about roughly 0.7. It'll make it a unit vector, and more importantly, it will be in the right direction. So let's go ahead and do that. I'm gonna write glm vec3 light direction is going to be -1, -1, and -1. But as I mentioned, I want to also normalize it. So there we go, there's our light direction. So since we determined earlier that it's the direction of the normal versus the direction of the light that we're trying to compare and see how much it faces the light, so the angle that it shares with the light, we really just need to figure out the angle between these two. But before we do that, there's also one little step that we need to not forget about, and that is the fact that the light direction that we've defined is a vector from the light to us. But we're going to be comparing this to the normal, which is a vector of where this surface faces to. So that's kind of like two different things. We have the incoming directional vector, and then we have an outgoing one. I'd like to compare it to both be incoming or outgoing. Outgoing makes more sense. So in other words, I'd much rather have a vector from us to the light instead of from the light to us. And that's really easy to do. I just need to negate the light direction, because that will obviously just flip it. And then once I have that, I can work out like the angle between these two vectors. And I can do that using a vector dot product. Because the cool thing about the dot product is it will tell us the relationship between two directional vectors. In fact, the dot product of two unit vectors is the same as the cosine of the angle between them. So what that means, if we write this down in our code, is that this kind of dot product between the normal and the negative light direction, since these are both unit vectors, is going to be the same as the cosine of the angle between them. And since the cosine function, of course, will give us a value between -1 and 1, same with the dot product. It will also give us a value between -1 and 1. And this value will determine how much our face, our pixel on our sphere, actually faces the light source. So for example, what happens if the dot product gives us 0? What if the result of our dot product is 0? Well, then that would mean that the cosine of our angle was also 0, and the cosine of 90 degrees is 0. Therefore, if our dot product returns 0, we know that the relationship between those two vectors, the angle between them, is going to be 90 degrees. That's actually perfect because if something is facing 90 degrees away from our light source, so if this was facing, well, 90 degrees, like that, you can see it's pretty dark. So really it's just the angles above 90 degrees which should get brighter and brighter until it's really facing our light source perfectly. And that is what we're going to use the dot product for. This D here is actually going to effectively be the intensity of our color. Now, obviously we know that if that angle is going to be greater than 90 degrees, the dot product will give us, just like the cosine of an angle that is greater than 90 will actually be negative. So because of that, what we're going to do is use GLM max, the dot product, and also 0. This is like a clamp, but it's only clamping one side of it. It's not gonna clamp it between two numbers, make sure it's between two numbers, just one. So we're making sure that it's going to pick the maximum of these two values. Since 0 is higher than a negative value, if this dot product is negative, then we will just get 0 instead. So now what we can do is we can take our sphere color, we'll go back to our original pink sphere color, and we'll just multiply it with this dot product. And if we run that code, check this out. How cool is that? We have our light source perfectly defined in the place that we defined it at. It's facing the direction we wanted it to be. And we now have some rather beautiful looking lighting hitting our sphere. So there you go. One small step towards photorealistic rendering. I hope that you guys enjoyed this episode. If you did, please don't forget to hit the like button. As an exercise, try and add some controls to this. Try and add something like to this IMGUI window that will let you control the color of the sphere, as well as the direction of the light. That kind of stuff is really fun to play with. And since this is in fact rendering, like in 6 milliseconds, rendering in real time, you'll be able to see that effect in real time as you play with the values, which is gonna be really cool and will hopefully help you understand this even more. And I really encourage you to play with this code for yourself. The code will be uploaded to the GitHub ray tracing repository, which will be linked in the description below. Next time, we'll be talking about cameras, how they work, and how we can have a camera system defined inside our application here. But until then, thank you guys for watching. Don't forget to check out Brilliant using my link in the description below, and I will see you guys next time. Goodbye.